Welcome to the second video of topic 7. In this video we're going to derive our big result, the residue theorem. In a Laurent series expansion of a function, the coefficient associated with the 1 over z term is called the residue. We'll see that the value of a contour integral that encloses a singularity is directly related to the residue for the Laurent series around that point. Extending to contours enclosing multiple singularities, we'll see that we need to sum the residues for the Laurent series at each singularity. As a quick recap of the previous video, we looked at how to identify and characterize isolated singularities, that was poles and essential singularities, and we characterized these by looking at their Laurent series. We saw that the order of a pole is given by the most negative power in the Laurent series, whereas essential singularities continue to negatively infinite powers of z. We also looked at relating zeros and poles of functions. The intended learning outcomes for this video are you should be able to derive and use the residue theorem to compute contour integrals. And you should also, importantly, appreciate that for contours enclosing multiple singularities, you need the residue from the Laurent expansion at each singularity in order to compute the contour integral. Let's begin.
This video is about residues. I'm going to begin by reminding us what Cauchy's theorem said earlier in the course. From Cauchy's theorem, we know that the value of an integral around a closed contour C is 0 if the integrand is analytic on and within that contour. We've seen in topic 5 that contours in multiply connected regions can be deformed through regions of analyticity, and that doesn't change the integral value. But what is the value of an integral in a multiply connected region? That's the question we're going to address in this video. So the question is, what value does such an integral take when the contour encloses isolated singularities, which are points where the integrand fails to be analytic? To start this discussion, let's write down the Laurent series of a function that has an isolated singularity. Let's suppose that some complex function f of z has a pole of order m at z equals z naught. We know from the previous video that this means we can write this function as a Laurent series, and m gives us the most negative power in that Laurent series. So here we would be able to write that f of z is the sum from n equals minus m to infinity of a n z minus z naught to the n. Okay, so this is our function that has a pole of order m at the point z naught. Let's imagine that we want to calculate the integral, which I'm going to call I, around some closed contour C of f of z dz. And here we're going to be considering that our contour C encloses the pole at z equals z naught. So I'm going to draw a picture. I'm going to dispense with the axes for clarity. Here is the point at which we have a pole of order m, And our contour C might look something like this, traversed in the anti-clockwise direction. This is our contour C. Well, we know that Cauchy's theorem allows us to deform this contour C through regions of analyticity without changing the value of this integral that I've labelled with a capital I. Let's choose to deform our contour to a new contour C' that is a circle of radius ρ centred at this singular point Z0. So this circle has radius ρ. And let's call the contour here C', which is also traversed in the anti-clockwise sense. I'll write down next to this picture what we've done. So by Cauchy's theorem, we may deform the contour C through the region of analyticity for this particular function that has only one singularity at z equals Z0. We're free to deform from C to C'. This resulting contour C' is a circle of radius ρ and centred at Z0. Okay, so this means that we can now write our integral as the integral along the closed contour C' of f of z dz. We're now going to substitute in our Laurent series at the top of the page. We can now write this as the integral along C' of the sum from n equals minus m to infinity of these powers dz. Because it's the integral of a sum of terms, we can integrate each term individually. This would give us the sum of these coefficients and then integrals of powers of z minus z0 dz. Now in fact we encountered precisely this integral in the third video of topic 5. The way we approached it was we performed a substitution. We let z minus z0 be rewritten as rho e to the I theta, and this allowed us to rewrite the differential dz as I rho e to the I theta d theta. And what we found, I'll write here from part 3 of topic 5, we found that this integral dz took two values. Either it was 0 if n did not equal minus 1. The only non-zero value was when n equals minus 1, and that value was 2 pi I. Returning to our integral on the left-hand side, this means that the only term that doesn't vanish in this sum is the term for which n equals minus 1. Therefore, we're left with our integral I is given by the integral around the closed circular contour C' f of z dz, and this is now going to be 2 pi I, which is the value of the integral when n equals minus 1, and then times this coefficient a minus 1. I'm going to label this particular coefficient. This is the coefficient of z minus z0 to the minus 1 in the Laurent series. This coefficient has a special name. This coefficient is referred to as the residue. of our function f of z at the point z equals z naught. So this is some very important terminology. We also sometimes write this for some short notation as res of the function f of z at the point z naught. I'll just note here that we showed, thanks to deformation property, that this is also true for our original contour C. Now this is a remarkable result, looking at this, this line, that the integral along the closed contour C prime of our function f of z dz is given by 2 pi I times this particular coefficient in our Laurent series expansion. This means we just need the Laurent series to determine an integral where the contour encloses a singularity. I'm going to put a red box around this because it's very important. And below I'm going to note that this result is core to something called the method of integration by residues. And I'm going to underline this as well. Let's do an example. Let's perform an integral that we didn't know how to do before. Let's consider integrating. Function f of z is given by cos of z over z cubed. And let's consider integrating it around any closed contour containing the origin. You note immediately that this function is singular when z equals 0. Well, we need the Laurent series expansion of this function, and we can do that using the series expansion for the cosine. So we can say to find Laurent series, we can write cos of z over z cubed. The expansion for cos of z is 1 minus z squared over 2 factorial plus z to the 4 over 4 factorial, and so on. Multiplying this out, we have 1 over z cubed minus a half times 1 over z plus 1 over 4 factorial times z, and so on. We don't care about any higher terms because they are all positive powers of z. In fact, the only one we care about is this one here, the term in 1 over z. From this, we can read off the coefficient a minus 1. The residue is minus 1/2. And that's really all we need to do. That means we can now write that the integral around the closed contour C that contains the origin of cos of z over z cubed dz, that's just given by using the expression at the top of the page. This integral is 2 pi I times the residue minus a half. So this integral is simply minus I pi. And it's really that easy. The next natural question to ask is what happens if there are multiple isolated singularities? So we'll ask what happens if the contour of integration contains more than one. isolated singularity. So let's imagine we have some function, have isolated singularities, at 2 points, z0 and z1. We want to calculate the integral around a contour enclosing those points of our function. As always, let's draw a picture. Once again, I'll dispense with drawing the axes for clarity. Let's imagine that our singularities at z0 and z1 look like this. This is z0. This is z1. And the contour C enclosing both of these looks something like this. Traversed in the anti-clockwise direction. Now, just as in the example above, we can deform the contour through the region of analyticity of the integrand. I'll write here that since these are the only two singularities, Cauchy's theorem allows us to deform the contour C. And I'm now going to take a copy of these singularities and put them down below. Okay, here's our copy. And let's draw a deformed contour. We've deformed the contour, so there's a circular path around each of the singularities, and these paths are joined by a channel. I'm going to label this path C0, this part of the channel as CA, this circular path as C1, and this one going in the opposite direction as CB. This doesn't change the integral value, which means that we can write the integral. The integral is now the integral around the path C0, the contribution along CA, the contribution along C1, and the contribution along CB. We're now going to do what we always do with a channel. We're going to take the limit of 0 channel width. What's this going to do? Well, the channel contributions along CA and CB are equal, but they are traversed in opposite directions, and so they cancel. I'm going to take a copy of this. And I'm now going to remove the channel contributions and close those other paths. I'll make a note here that the channel contributions cancel. We're left with these closed circular contours C0 and C1, and this is exactly the situation we had earlier when we showed that these integrals can be performed using the method of residues. I'll write below. These are now just two independent cases of valid residues, as before. And that means that we have our integral I, which was the integral along that original contour of our function, is now given by the integral contribution along the circle C0 plus the contribution around the circular closed integral C1. Using our result and our notation from above, we know that these integrals are given by 2 pi I times the residue of our function at the singularity Z0, and then this second one is given by 2 pi I times the residue of our function at the other enclosed singularity Z1. So we've seen that an integral along a contour enclosing 2 isolated singularities can be decomposed into the sum of residues in this way. And in fact, this argument generalizes to an arbitrary number of isolated singularities. I'll write here that this argument, namely deforming your contour and cancelling contributions along channels, generalizes to any number of isolated singularities. Let's denote them as a set of points zk. As a result, we can write that the integral along a contour C that encloses these singularities labelled zk, this is going to be given by 2 pi I, the sum of the residues at all of the enclosed singularities zk. This is the residue theorem, or the method of integration by residues, and it's an extremely important result that we're going to be using for the rest of the course. I'll put it in a red box. Taking a step back, this is an extraordinary property of contour integrals. It says that only the properties of the enclosed isolated singularities matter. As long as you can find residues for poles or essential singularities, you can evaluate contour integrals where the contour contains those singularities. Let's go through an example. Let's consider evaluating the integral along a contour C of 5z minus 2 over z times z minus 1 dz, and let's specify our contour like this. Let's say it is the set of points z that have distance from the origin 2, in other words, a circle. As always, let's draw a picture. We have real and imaginary. And let's draw our integration contour. Here's our integration contour. C traversed in the anti-clockwise sense. The point here is 2i minus 2i, 2 and minus 2. Okay, let's look at the singularities of our integrand. Well, our integrand has isolated singularities at z equals 0 and z equals plus 1. And you can see that by looking at when the denominator equals 0. Let's draw those singularities in our picture. We have one at the origin, and we have one at the point 1. Now, both of these singularities are enclosed by our contour. That means we need the residues at both of these singularities. We need residues at z equals 0 and z equals 1. This means that we need two Laurent expansions. Why is that the case? Well, when we do this shrinking trick above, the circular contours end up lying in the neighbourhood of each singularity. And that means that you need the Laurent series in that neighbourhood for you to get the correct residue. I'll write that down here. Note that even though we're integrating around a path where the distance of z from the origin is 2, it's vital that we use the Laurent series in the neighbourhood of each singularity. And I'll make a note that that's related to our shrinking to circular contour trick earlier. This is a really important point, so I'm going to underline it. That you need the Laurent series in the neighbourhood of each singularity. Let's first deal with the singularity at the origin. The neighbourhood that we care about there can be written like this, where we are expanding about z equals 0. This is precisely an annulus of analyticity that we encountered in the previous video. Right, let's get around to expanding this. We have 5z minus 2 over z, z minus 1. This can be written as 5z minus 2 over z times minus 1 over 1 minus z. You'll recognise this term on the right hand side as an infinite geometric series. We can write this now as 5z minus 2 over z times minus the sum from n equals 0 to infinity of z to the n. Writing out the first few terms, we have 1 plus z squared, and so on. Multiplying this out and simplifying some factors, you can check for yourselves that we obtain 2 over z minus 3 minus 3z and terms which go as z squared. This is our Laurent series for the expansion about the point z equals 0, and you can read off the residue as the coefficient for the 1 over z. That means that the residue for our function at the origin, the singularity at the origin, is 2. Next we need the Laurent expansion about the other singularity at z equals 1. So that neighbourhood is described by this expression. We're going to let epsilon equal z minus 1 and expand in powers of epsilon. We have 5z minus 2 over z minus 1. This will give us 5 lots of 1 plus epsilon minus 2 over epsilon times 1 plus epsilon. We can tidy this up as 3 plus 5 epsilon over epsilon times 1 over 1 plus epsilon. Just as above, this is yet another geometric series. We can write the first bit as 3 over epsilon plus 5. And now let's take out the first few terms of this infinite geometric series as 1 minus epsilon plus epsilon squared, and so on. Multiplying this out, we have 3 over epsilon plus 5 minus 3 minus 5 epsilon plus 3 epsilon, and then all higher terms are going to be of the order epsilon squared. Finally, let's substitute back in terms of z, and this leaves us with 3 over z minus 1 plus 2 minus 2 times z minus 1, and terms in z minus 1 squared. This is our Laurent series, and again we can read off the residue here as 3. Therefore, the residue of our function at the point z equals 1 is simply 3. Okay, we've got the residues we need. Now all that's left to do is to substitute them into the residue theorem in the red box. We can write, so by the residue theorem, the integral along our contour C, 5z minus 2 over z times z minus 1 is given by 2 pi I times the residue at this enclosed singularity and the residue at the other enclosed singularity. Substituting these in, we get 2 pi I times 2 plus 3, which leaves us with the solution 10 pi I. And that really shows the power of this method of integration by residues. That's the end of this video. As a quick recap, we've shown that integrals along contours enclosing isolated singularities can be evaluated using the value of the a-1 coefficient of the Laurent series, and that's called the residue. We did that by using our earlier result for the integrals of powers of z minus z0 around a circular contour, and also the deformation property in multiply connected regions. The residue theorem is extremely useful for calculating integrals in an elegant way, and in the next video we'll look at methods of computing residues. So that's next up in the third video of topic 7. Thanks for listening.